All right. Welcome back to our video number 12, which is going to be kind of a more interesting video where we're looking to kind of like branch out from what we've been dealing with was linear systems. So we're going to start looking at nonlinear systems because even the very simple systems that you have around the world, they tend to be nonlinear, even though for the most part, the nonlinearity might be very, very small. And then we can say, hey, it's mostly linear, so I'm going to use linear theory. But nonetheless, that small nonlinearity could potentially may have a very large effect on the system. And as such, we want to make sure we are able to deal with nonlinearities in the system. So that's what we're going to be doing today, where we're kind of going a little bit further than essentially just assuming all of the system dynamics are going to be linear. So we are going to not go too much detail into nonlinear system theory here. Rather, what we'll do is we'll look at the system and then figure out how to linearize the system. And then we're like, hey, I know how to once the system is linear, I'm an expert. Hopefully, you are too, on applying theories and kind of Kalman filter on the linear system. So essentially, once we kind of like essentially twist and massage the nonlinear system into a linear system, we can then apply the linear Kalman filter theory and all of the other stuff that we know so far. So that's what we're going to be focusing on in this video. So the learning objective is going to be the application of Kalman filters to nonlinear system. So we'll do a quick recap and we'll talk about linearizing nonlinear system model and then introduce to EKF, which stands for extended Kalman filter, and then we look at discrete time or digital extended Kalman filter. So let's quickly recap what we've done so far. In the previous video, we had covered discrete time and continuous time Kalman filters, but for linear systems. So the Kalman filter, for the linear system at least, aim to minimize the covariance of the estimation error. So essentially, we have the system, and then you had measurements that are coming in that's being affected by the noise, and then you have the system itself. So and then there's a distribution of likelihood of what the actual values of the system would be. So then what that means is you can calculate the covariance or the kind of the expected value of the square of the estimation error. So the Kalman filter try to minimize it. So what it will do is, so if you have a distribution, it's going to try to make it narrow and narrow. You can never actually make it completely zero, or you can never make the error to be completely zero. The best you can hope for is to make the covariance as small as possible, but you have to be aware that that doesn't really completely preclude the fact that there's a very low probability that the system errors might be larger than the envelope that you're actually visualizing, simply because anytime you have a distribution, what you're actually looking at is the probability. So you can say the likelihood that the system might be some very far away from the actual estimation is reasonably low, but you can't really completely eliminate it. And the hope is, as you'll run the Kalman filter long enough, everything kind of like becomes nice, and the system is indeed where you think it's. So that's the kind of the hope or the philosophical aspects of dealing with uncertainty in the context of control systems. We have to be a little bit aware of the assumptions that we made. So we assumed that the system model was linear and was perfectly known. So I did mention that there are some issues when there is some uncertainty in the model, or the model has a higher dimension than the actual model that it used. So there is some discussion in the book. And the other assumption is that the noise that's affecting the system are all white, zero mean, uncorrelated noise sequences, or noises in the case of continuous system. So if any of these conditions are violated, there is a potential for the Kalman filter to diverge. So what we mean by diverge is that you may think you're actually following the trajectory, but your system might be much further away than what your estimate is. So just imagine you're going to a foreign country and then you're following your friend, everybody's wearing the same shirt, and then you kind of start following a wrong person. So then your estimation error is fairly large, and it's not really good for your system. there's a probability that if your controller is based on your estimate, then it's thinking that it's doing a pretty good job, but in reality the system might be going haywire and might eventually blow up in the worst case scenario. So that's the disadvantage. We need to make sure that the Kalman filter and all of our estimates do not diverge. So first, let's look at a general representation of a nonlinear system, and then we look at how we can potentially linearize that system. So in general, because of the way the nonlinear system is set up, you could have a lot of complicated terms. So you could essentially have like x squared, x times the input, x times the noise, and then you can have any combinations possible, kind of like higher powers, tan, cos, and anything you can imagine under the sun. So what happens is you can actually, rather than just it being represented as a matrix product, we typically just write x dot is equal to some nonlinear function. Similarly, we say y could also be potentially a nonlinear function of the states, and also it could change with time, and then there is a noise that's affected. And we don't really make any assumptions or comments regarding how things are multiplied or what's going to happen inside the H. Just we have to remember that any model that we have can be kind of like massaged essentially into this particular model. So an example would be is if you think about your normal linear state space model, I can actually say my f is ax plus bu plus w, because I had x dot as ax plus bu plus w. What I can do is in that case I would represent my f as being equal to whatever was coming to the right hand side of the x dot. Similarly for y, I can just say h was equal to cx plus v. So that's essentially what we're doing. This is just a more generalized representation of what we had done for the linear system. So we here again, So here again, we could have as many states as possible, in which case you would have as many equations here. So this would essentially be vector equations here. And then if you had multiple sensors, again, these would be vector equations. So you could have H1, H2, and so on and so forth corresponding to each of your sensor. So an example would be, so imagine you are having a viscous drag. So essentially, if you imagine the drag force that's acting, say, when you're driving the car, it's actually proportional to the velocity squared. And then there is a constant, which is the drag coefficient. So we can give drag as minus CD squared. So obviously, because there's a square term, you can't actually make, or you can't, like if this drag term is there in your model, there is no way you can actually represent it as a matrix, or you can't represent it inside a matrix simply because it's a square and you can't represent a square using a linear value. So let's look at a more fully formed example. So imagine you have a spring mass damper, but rather than the damper being linear, there is actually a viscous drag in the damper. So what will happen is if I'm measuring the position of the mass as x1, and then I say x1 equal to y, x2 is x1 dot, which is the velocity of this mass, and then what's happening is the force acting on the mass is going to be proportional to the spring times the displacement, which will be the spring force, and then the damper or the viscous force is going to be minus CD, and then the square of the velocity, which becomes x2 squared, and then there's potentially a noise that's occurring over here. So in this case, we are also just imagining that rather than have a linear sensor, you have maybe like a magnetic sensor or some other sensor which actually saturates, and we have the equation that the saturation is tan h times x1. So this function, if I draw it, was going to look something like this. So this is going to be my x and y axis. So this function is going to go past the 0, and then it saturates past a particular value. So this is the assumption for my sensor over here, and we would potentially have this kind of an option over here. And in this case, what we can actually do is write the f as follows. So I have to write, because it's going to be a vector equation, the first row of f needs to be equal to the derivative of x1. So if you look at here, that's going to be x2. The second one is going to be coming from here. So if I divide this equation by the mass, and I'm going to have k over m, and then cd over m, and then 1 over m times w. So this equation just becomes m inverse times f minus k x1 minus cd squared, cd x2 squared plus w. And so this is the nonlinear equation. And in this case, the y is going to be tan h x plus v1. So essentially, this is the nonlinear equation that's being represented as an example here. So now we do have fairly complicated and more sophisticated computer systems, right? So there is nothing stopping you from actually implementing as complicated a model as possible in MATLAB with the hopes of it simulating the whole system. So for instance, we do a lot of work where we have developed newer models for fuel cells, wind turbines, and so on. And then we have powerful computers, even in fact, even my desktop and even my laptop can actually run a lot of these simulations. And if we needed more powerful computers, we can always use the Westgrid computer or like a computer cluster to do the simulation. So the simulation itself is not that big of a problem. The problem comes when you want to do some more interesting sensor fusion or essentially do like a Kalman filter or some other techniques on the nonlinear model, where we find that the actual theory that's available is fairly lacking. So what we need to do, at least in this part, is we are going to look to approximate the nonlinear function. So obviously, if my function looks like this, so this is an arbitrary line over here, there is no way I can just represent it by a linear, which is going to be like some proportional or something of the sort, using this curve over here. So what I'm going to do instead is I'm going to imagine what's going to happen here, keeping in mind that I can't actually get a linear model to fit the whole range. But what I can do is, if I look at a very, very small neighborhood, irrespective of where we are, if I take a sufficiently small neighborhood, I can always find a straight line. So for instance, if I zoom in enough around this point where I've drawn the line, this looks straight enough. Maybe there's a little bit of a bend, but then I can't actually see it within the resolution I have here. And if I basically choose a small enough neighborhood, the line is always going to be straight within my errors and within my error bounds or within the accuracy I'm looking for. So we are actually going to use this information to kind of essentially do a linear analysis in small segments of the model, of the nonlinear system. So for this, if you look at the model, at any point, I can basically say, if I wanted to calculate the x within that small neighborhood, I can basically say it's going to be the f at that value and plus slope times x minus x0. So for instance, if I wanted to figure out what the value of f is here, I tell you what the value of f is at the middle. So what I can do is, if I know how far I'm going, and then I can use a linear approximation, and then since I know the slope, I can calculate what this value is going to be. So this is what we would do. So we can potentially include higher order terms and then get a more accurate value. But the more general way of doing this, rather than just like trying to figure out what the slope is, can be done using what's known as a Taylor series linearization or Taylor series approximation. So you can do the Taylor series approximation about any point. So we choose to do it about the x0. In that case, if I have a nonlinear function over here, so what I'll typically do is, this is going to be, so this is a vector function, and then it's a function of x, u, w, and t, right? So what I need to do is, if I wanted to find what I'm looking for, is rather than it being just like on a linear scale with respect to x, I could potentially have different directions for x, and then I can also have different u's that I want to calculate the derivative with respect to. So what I'll do is, I'll take this function and then take the derivative with respect to the different x's. So that will be the partial derivative of f with respect to x. And then I do the same thing with respect to u. And what I would essentially form is, I would form a matrix equation. So essentially f is going to be a column vector. And then if I take the derivative with respect to x, I'm going to form, with respect to x1 would be the first columns, x2 would be the second column, so on and so forth. And similarly with respect to u, and then I can write it this form. So f, this will be f at the 0 point plus the slope with respect to x times x minus x0 plus the slope with respect to u, which is the partial derivative of f with respect to u times u minus u0, and then similarly with respect to w and w minus w0. Here the delta is the partial derivative, and what that means is I'm taking the derivative only with respect to that particular variable. So the partial f partial x means I'm taking the derivative of f only with respect to the x's, keeping everything else constant in that equation. So similarly, we can do a first order approximation of the h. We can write that as h at x0 comma w0 plus partial h partial x at x0 u0 and so on. So that's just written as 0 here times x minus x0 plus the partial h partial v times v minus v0. So what we can then do is we can write my f as the approximation of f at the 0 point plus some A matrix times delta x plus some B matrix times delta u plus some L matrix times delta w. So where A would be partial f partial x at 0, B would be partial f partial u at 0, L would be partial f partial u at 0. So when I say at 0, I mean x equal to x0, u equal to u0, and w equal to w0. Similarly, we can do that for for h, and this is the formula that we would get. So let's try an example. So we have f is sine xu plus w, and then x hat or x is pi over 8, and then u equal to 0, and then calculate the first order Taylor approximation for f at x0, u0, and for w equal to 0, and then you're also going to calculate the value of f at a small increment. So we're basically doing 1.1 times x0, which is about a 10% increment, and then 10% increment on u, and then you're going to compare the result with the actually substituting the values directly, and then see what's actually going to happen. So now would be a good time to pause the video and then do the calculation. So the Taylor series linearization is going to be taking partial derivatives over here. So we say f at x comma u would be f at x0 u0 plus the partial with respect to f, and then x minus x0 partial with respect to u minus u0, and then w is kind of fixed over here. So let's calculate these values. Since I have sine x times u, so the way I would calculate this, or rather if I basically calculate this value first, I get this is equal to, you can calculate this value and then see what happens. So this would be 1 over root 2. And then we can use chain differentiation. So for instance, if I wanted to calculate the derivative of dfd of z of x with respect to x, I do it with respect to z first, and then differentiate z with respect to x. So in this case, I take the partial derivative. So I take the derivative of sine first, so that becomes cos, and then I take the derivative of for d partial f partial x. I'll take the derivative with respect to x, and so I'll end up with u. And then if I did the derivative with respect to u, I'll get x. So partial f partial x at 0 would be partial sine xu divided by dx partial x at 0. If I take the derivative of sine, that becomes cos, and then I take the derivative of xu with respect to x, I get u. So I get, this is the value, I get sine xu times u. Substituting in the values, I get 2 times pi over 8 times 2, and so this comes to 0.7071 times 2, or 1.414. So if you similarly take the partial of f with respect to u, we end up with partial f partial u would be sine xu with partial sine xu partial u at 0. And then if I do the partial here, this becomes sine xu, and then I take the partial of xu with respect to u, I'm left with x. So I get cos xu times x, which if I say would be equal to 0.7071 times pi over 8. So again, I'm substituting cos pi over 4 times pi by 8, and this comes to 0.2777. So now if we substitute this back in the Taylor series, since my f at x1 u1 is given by this formula here, so I'm going to substitute in these values. So this comes to sine pi by 8 times 2, plus I just calculated this to be 1.413 times x minus x1, x0, which is basically like 1.1 times pi by 8. So that becomes 1 minus 1.8 will be 1.1 minus 1 would be 0 0.1 times pi by 8. And then again, df partial f partial u, 0 was 0.2777. Again, this is 1.1 minus 1 will be 0.1 times 2. So this is what I get. So if I evaluate this, I get to 0.8182. So this is a fairly complicated way of coming up with the same solution. But let's see what happens if we substitute in the direct value of 1.1 times pi over 8 times 1.1 times 2. So direct calculation, this is a value. So if I substitute in, this comes to 0.8136. So there's still some error, but then this is a little bit easier. It's fairly close, so our approximation works. So again, this looks like a complicated way to get to the same result, but you can imagine if I had to repeat the same thing for say 1.05, and then instead of calculating a direct calculation, I actually have a linearized formula which is much easier to calculate and quicker to calculate, even if you have a more powerful computer. So this is what is the kind of the crux of what we're doing with respect to linearization. So let's actually now look at the EKF, or the extended Kalman filter. So we are going to go back to our nonlinear equation over here. X dot is f, and then y is h, w and v are zero mean noises, zero mean Gaussian noises or processes. So what we do is, since we know how the system is going to evolve, what I can do is I can say I'm going to make it as x dot is f, substituting in the same values. So we are assuming we know the input u, so that goes in here. Since I'm estimating x, so I put an x hat over here. The best estimate for w is going to be 0 because it's a zero mean process. And then we have k, which is going to be kind of the linear gain that we give, minus h. And then again, you have x hat, the mean or the expected value of v is going to be 0 times t. So what we then do is define our error x tilde as x minus x hat. And then if I take the derivative, x tilde dot is going to be x dot minus x hat dot. So here I'm going to substitute in for x dot from this equation over here, and then x hat dot from this equation. So what will end up happening, if we group them together, we get f minus f with the x hats, and then we have this k term over here. So this becomes f minus f hat minus k minus y minus h hat. So where f hat would be the f with the x hat, and then h hat would be the h with the x hats. So we have this. So now let's keep moving forward. What we do is this equation over here, what I can do is expand it, kind of like linearized or Taylor series expansion of this term about x hat. So this basically becomes f x hat, so that term is going to cancel out, plus df by dx times x minus x hat, and then plus df by du, u minus u, because the same u appears in both places, and then partial f partial w, w minus 0. So if I clean this up, I can actually write this as a x tilde plus lw. You can do the same thing here, where I have y minus h x hat. This becomes h minus h x hat, and then I take the partial with respect to x. We have the h0 term that gets cancelled out. So this, and then so we get partial h partial x, x minus x hat, partial h partial v, v minus 0, and then we can write this as cx tilde plus mv, where a is this term partial f partial x, l is partial f partial u, or you can think of it as being like the b term will just cancel out. C is going to be partial h partial x, m is going to be partial h partial v. So this error dynamics is actually almost equal to x tilde is equal to ax tilde plus lw minus k, cx tilde plus mu. So the only thing that changes is, instead of us having w, we're multiplying by a constant, and then similarly instead of it having just v, so we're multiplying that by a constant. So correspondingly, our covariances would get scaled up by these matrices. So the system equation then becomes that we have the x tilde x dot is the normal system equation. X hat, we set it to the estimated value of x0, and then p0 again the covariance of the error. So we calculate at each step these partial derivatives, and we use the equation very similar to the Kalman filter. So if we compare this equation, we notice that instead of r, I'm using r bar over here. Instead of q, I've used q bar. We'll just see what these are. But other than that, the equation just is p dot is minus p c transpose. Instead of r inverse, I have r bar inverse, and then cp plus pa plus a p a transpose. Sorry, ap plus pa transpose plus q bar, and then K is just P C transpose R bar inverse. So here my Q bar is going to be L Q L transpose. Again, because we are doing essentially like an inner product, our Q gets multiplied by L and L transpose on either side. Similarly, R bar is going to be M R M transpose. So then our estimation is still going to be very similar. We still run this with the same system model, and then we have the update based on this K over here. So let's do this example. So this is essentially like an extension of the problem that we just had. So where we have f is sine xu plus w, and then x bar x hat is 0. X hat at 0 is pi over 8, and then u is given to be 2. Just the addition thing we have is y is tan h x plus v, and then we have given the noise covariance w is 0 mean with a Gauss with a covariance of 1, v is 0 mean with a covariance of 2, and then p is defined as the expected value of x minus x hat squared, and then p0 is given to be 0.1. Then we are required to calculate k and p dot. So the hint we're going to use is the derivative of tan h with respect to x is secant squared secant h squared x. So now would be a good time for you to pause the video and then redo the calculation, and then you can come back and verify your answers. So we can steal the some of the values from the previous problem. So for a, which is partial f partial x, so we can basically get that from the previous value, so that it came to 1.414, and then partial f partial w, because w is just here, becomes 1. So we'll define h, so which is just going to be tan h x plus v, and then we take partial h partial x to get c. So this is basically going to be secant h squared x. So this is hyperbolic tan, and then this is hyperbolic secant. So this is the secant h squared of at pi by 8 plus 0, because again we substitute v equal to 0, and then this comes to 0.8604. So we do the same thing for m. So m is partial h partial v. Again, because of the way this is set up, so this actually comes to again secant h squared pi by 8, which is also 0.08604. Sorry, 0.8604. Our q was 1, r was 2 from the problem. So q bar is L Q L transpose. So this comes to 1 because L Q and L transpose are all 1. R bar is M R M transpose. So this becomes 0.8604 squared plus times 2. This comes to 1.4806. So we can substitute and calculate the value of k, which is P C transpose R inverse. So P we calculate is given to us. C transpose we just calculated. It was actually equal to the same value as here, 0.8604. And then R we just calculate over here. So this comes to 0.1 times 0.8604 times 1.406 inverse. This comes to 0.05811. Similarly, we can calculate P dot, which is minus P C transpose R bar inverse CP plus AP plus PA transpose plus Q bar. Again, here for this case, the transpose is the same as the actual value. So if we substitute this comes to 0.1 squared, which is corresponding to P squared from here and here, 0.8604 squared from C and C transpose times 1.406 inverse, that comes from R bar, plus 2 times A was basically P was 0.1, and then A was 1.414, and then Q bar was 1. So if we substitute this, it comes to 1.2778 is my P dot. So this basically concludes our discussion on continuous time Kalman filter, extended Kalman filter. This kind of essentially we are linearizing the model, and then we looked at how we can calculate the K and the P dot. So once you have P dot, so if you imagine you just move a little bit forward in time, you can calculate K again. So this would basically be implemented as a continuous integral, and then K will be continuously calculated, and the whole estimation loop would be marching forward in time. So next we move on to digital or discrete time extended Kalman filter. So here we have the system model over here. Instead of it being a derivative, there's going to be time step. So we have a similar model where xk plus 1 is some nonlinear function fk time, and then it's a nonlinear function of the states, the inputs, and the noise. The sensor measurement yk is also another nonlinear function given by hk of x comma vk, and then we are given that the noises are zero mean Gaussian and they are uncorrelated as well. So these are kind of the standard assumptions of the Kalman filter. The only difference is instead of a linear model, we have a nonlinear fk and a nonlinear hk over here. So to calculate the a priori estimate before we do anything with the Kalman filter, what we actually do is use the nonlinear model. So again, what I've done is instead of k plus 1, all of it is reduced to k. So notice everything, so k becomes k minus 1 and so on. So nonetheless, this is the same model. Here wk would be assumed to be 0. And so what will happen in this case is we basically would get the k up. To do that, we basically linearize the model. Capital Fk would be the partial of Fk minus 1 at xk, and then you evaluate the derivative at xk equal to xk x hat plus k minus 1. Uk should be known, and then Wk would be zero mean, and then we similarly evaluate Lk at x hat plus at k minus 1, Uk minus 1, and then 0. So keep a note that this is evaluated at x hat plus at k minus 1, and then uk minus 1 and 0. So we have a similar equation for the posterior estimate. To calculate the covariance, we calculate pk minus as fk, pk plus k minus 1, which is assumed to be known from the previous step, and we'll also see how it's calculated sequentially. And then we have, instead of q, we have q bar, where q bar is lk minus 1, qk minus 1, l transpose k minus 1. So the only difference would be instead of q, you have a q bar, and then we evaluate hk and nk at x hat minus. So because you already calculated x hat minus, just to get a slightly better estimate, we do that. And then kk is going to be this equation over here, where r bar is mk rk mk transpose, and then k plus k plus is I minus k k hk pk minus, and then we kind of just update the x hat plus at k using this equation. So the book actually uses multiple steps to do these estimates, so I recommend you go through it, and it just makes it a little bit more accurate, but this is kind of the gist of the extended Kalman filter. So this basically concludes our discussion on the extended Kalman filter, as well as the both for the digital and as well as the analog extended Kalman filter. The basic idea is the concepts kind of remain the same as the linear Kalman filter, just that we kind of like linearize the nonlinear model about either the equilibrium point, if we know for sure what the equilibrium point is going to be, or we linearize the model about the estimate. So as the Kalman filter kind of is tracing the model, we kind of do a linearization and then use that to actually calculate all of the parameters for the extended Kalman filter. So what this means is for the linear case, you remember we talked about a steady state Kalman filter. we can't really apply that to the extended Kalman filter, because the extended Kalman filter, essentially the partial derivatives of f and all of the other things actually trace and are dependent on the estimate, and the estimate would not reach a steady state. That means we cannot really define a like a steady state value of the extended Kalman filter. So the other thing that happens is when you're actually linearizing the model, there'll be like small errors that are introduced. And depending on how close your x hat is to the actual value of x, these errors might actually play a significant role in the stability of the overall stability of the system. So although it's looks like it's easy to just like linearize and then let the computer take care of all of the other issues, it's not always that practical or easy to implement in practice. And also what you need to do is at each step, you're actually calculating the partial derivatives, which are also known as the Jacobian of the system, which again adds the computation time, particularly if you're implementing it on a microprocessor or a small processor. So in summary, so although this is a good, strong method to extend the Kalman filter to nonlinear system, in practice, this may not always be possible, and you might need to do more interesting analysis, either using H infinity nonlinear observers or uncentered Kalman filter, which would kind of give a better estimate and kind of better result. So this basically concludes our video, and thank you for watching.